you have data and you have models, right? And the vast majority, or the point, a lot of what we do in astrophysics is we try to do, well, two things. One, we try to understand what is the nature of the sources of the objects that we study. And I will call that kind of model selection, right? So this is the hypothesis testing that Peter was talking about yesterday. I want to know, is this a supernova, is this a TDE, or what have you, right? So this is the question of computing things like odds ratios. He was showing these ratios of Bayes factors yesterday. In this case, for he took the example of the GRB with the claimed kilonova component from some number of months ago, and he had plots with like it was like -1 to -10, and sort of the odds ratios there. And then the second thing we do is what we call parameter estimation, right? So I have a model. That model has a number of parameters, and I want to use the data that I have to constrain the parameters at hand, right? And so the way I kind of think about how a lot of this works is I will go to the literature, or I will, go to my friend with, simulation software to be able to, simulate something like a kilonova. And I will want to know what is the amount of ejecta that this particular, compact merger has, or, what's its, orientation angle to meet and such. And in order to answer that question, so the notebook will walk through a particular example. Unsurprisingly, given what the group here does, it talks mostly about GRBs and kilonovae. But I just want to emphasize that there's no, all of this absolutely applies if I study TDs, supernovae, all this stuff, right? I will start with some piece of code, so in this case, we introduced this, this nuclear multi-messenger astrophysics framework. But for example, SN Cosmo, MOSFET, there's a wide variety of open source frameworks that do either, synthetic light curve generation, it will implement, a variety of, supernovae, TDE, whatever models that you have. And sometimes, and I will say even often, will include samplers as well, right? And so Peter talked about yesterday how you have both Markov chain Monte Carlo and nested sampling algorithms out there, a billion of them at this point, right? You type in, you Google, MCMC, Python, these days you'll get 1,000 different hits. And most of these frameworks under the hood will call these various samplers. Maybe they will do some amount of, tuning of the, the configuration, kind of, do some of that for you. But the truth is that, at least for the vast majority of the time, it doesn't really matter what you end up choosing, right? The main job that you have is, how do I identify the data that I care about? Putting together good data is hard, right? However, as we talked about in day one, we have data from ZTF. I mentioned, of course, that there's a variety of open data sets at this point. Some of the folks in this audience have written modules to grab all sorts of data sets. And then the second is you need to decide what are those synthetic light curves that you're comparing things to, right? And so the notebook in this case will walk you through generation of some kind of light curve. Yeah, so this is a I guess this is a kilonova, in this case an I band in ZTF, right? And so this is what I'd call a light curve, right? So we have absolute magnitude on the y-axis, we have time on the x-axis, and we show the evolution in this particular passband over time. Now, most of these frameworks, and I think this is mostly true, SN Cosmo in particular has a wide variety of popular filters that are, let's say, super prevalent in at least optical astronomy these days. And so if you just were to Google SN Cosmo built-in bandpasses, right? So what is kind of the great challenge here is how do I go from model to data? Well, usually when I'm given a model, I'm usually given a spectral energy distribution as a function of time. That is almost always what I will receive from some theorist, right, or someone who's doing modeling. The vast majority of the time, though, you will be dealing with photometric data sets. This is not always true, right? There are quite extensive spectroscopic data sets for wide variety of transients, but in general, at least as we talked about on day one, as these data sets have grown, ZTF or GoTo or Atlas or whatever, you're inundated with photometric data. And so you need to convolve that SED that you receive from your modeler friend with the band passes of the survey that you're using. And so, of course, there's a wide variety of frameworks that take care of this for you. I just wanted to highlight this point that SN Cosmo in particular has a lot of them, at least the most common ones available. These days, me, Igor, others pretty regularly open pull requests against SN Cosmo to add new band passes. I think we just did GoTo recently since they've been posting public data sets. And so this may be one of the most annoying remaining hurdles that goes from doing this hypothesis testing. It's just keeping track of your filters. But even that has become pretty standardized at this point. And so the idea is that once you have your SED, and it's too bad, I should have plotted the original spectra as a function of time for, in this case, this kilonova model to show beforehand. But once you have the SED in hand and you have the filter bandpass that you have in hand, you have SN Cosmo and its nice built-in tools, you can produce these light curves. And so the notebook will, and I encourage people to take time to do this. So, this was a kilonova up there. This is, some kind of supernova. It gives you a few tasks to just basically produce these synthetic light curves based on these open source packages, which is fine. At the end, then, yeah. So the let's see if I have. I wanted the nice light curve that's from Peter's paper. So Peter showed this in his talk yesterday, but I just wanted to kind of remind folks. So what happens then, you have your synthetic model, you have your kilonova grid, you have your way to translate your spectral energy distributions into common pass bands, and then you can create synthetic light curves, in this case for some kind of kilonova model, right? And then you need the data that you have on hand, right? And so in this case, we've within NMMA, we have a set of example data that you can play around with. This is a curated set from GW 170817 that we've been using for a handful of years now. And so this is what one of the examples that the notebook has you walk through. As I said, this aspect, which we don't really talk about in the notebook, this is actually the most painful part. How do I get the nice photometry that I have, right? But this is, we're sort of assuming that you've made the effort to, go to an alert broker and download your data sets and put it in a format of this kind. If folks do have particular transients that they're interested in and they are struggling to do this, there are people in this room who can help you. There are folks who are writing PhD theses on, weird ZTF transients. So there's, a lot of data out there that's available to you that you can try out a variety of models on. But at this point, you're almost done. You have your data, you have your model, you have chosen your Bayesian sampler, you've chosen MC or pi multi-nest or whatever. And at that point, then see if I can go back to my notebook. At this point, then your sampler is going to output posterior distributions, right? And so what are these, right? These correspond to contours in likelihood space, like where all of the points in the parameter space are equally likely to fit that data for the model that you have, if that makes sense. So the idea here is, right, I have data and I have a model. However, there's a lot of degeneracies, right? There's a lot of different kilonova parameters, compact binary parameters that will fit these data, right? There's not one unique solution, right? And so what this Bayesian sampler is doing is efficiently trying to sample the space to identify all of the different configurations of this particular model that fit your data, right? And so these histograms or these distributions are just marginalized versions of that, right? Where I have taken all of the points in the parameter space that my sampler has identified as being consistent with the data that I have. You make a histogram of each of these parameters. So this is the distance, this is the this is some kind of opening angle, this is the inclination, time, some ejector parameters, and so on. And so what we're really reporting is we report these marginalized distributions that come from all of the points in the parameter space that are, approximately equally likely, right? And so this is what it means when we make a corner plot, or when sport folks kind of throw around this term corner plot. What they're really meaning is tell me what these marginalized distributions look like that fit my data. And so the notebook, walks you through how to do that. It also shows, I guess, some examples if you want to even do this jointly between electromagnetic data and gravitational wave data, which is fine. This workshop's.
There's a question on there.
Can you tell them to? I guess I can mute. Yeah. So.
Can you repeat the question?
Yeah, of course. Okay, so the question is, let's imagine that I have my own model. What is maybe the best way to see this implemented, right? So it's a little up to you. So at least, so our group maintains NMMA, and we have a wide variety of kilonova, supernova, other models in there. And we absolutely accept pull requests. And the only thing that your model needs to really do is, given one of these SN Cosmo passbands, given something on this list, return some kind of light curve, right? And so the one path would be, especially if it's sort of fast transient based, it's the kind of thing that makes sense to put it into NMMA or something like that. However, probably even simpler is SN Cosmo itself. I don't know if folks know about SN Cosmo, but it's a pretty popular Astro package that implements a wide variety of models. They have their own samplers inside. It's mostly designed to do supernova cosmology, but is expanded over the years since then. Yeah, since it was first written. They have a, I think they call it spectral time series class, and all that takes is time, wavelength, and SED in ergs per second per hertz or something like that. And then you can use the standard SN Cosmo. They have, some very straightforward samplers. You can just look in the docs. And so my suggestion would be to, depending on what you're doing, talk to us, right? I think we would be happy to, I would love to see more models in NMMA, for example, not to plug our own stuff, but SN Cosmo makes it very straightforward to do this. Now, probably a third option, and maybe this is, depending on who you are and what you're doing, this might make the most sense, but actually doing this, like writing, let's say, a small sampler by hand is relatively straightforward, right? What do I need? Well, I need a prior and I need a likelihood, right? So Peter was like, you take a prior, you take a likelihood. So the likelihood for, the vast majority of, let's say, in the optical at least, right? So we have our data, we have our model, or what the model predicts given some set of parameters, right? So as Peter was talking about, we have theta, which corresponds to the various parameters of the model that you have: distance, inclination, ejecta, sort of everything goes in your model. From that model, you can predict a light curve, or you can predict a magnitude, take the difference between your data and your model and divide through by the error, right? Usually this is the error in the data itself, but sometimes you have error in the model itself, and so you have some kind of square root of sigma squared thing that's going on. But then this is just a Gaussian likelihood where you multiply for every data point that you have, you're multiplying these terms together. Well, it becomes a sum because there's a log, and that's as simple as a likelihood ends up being. You can write this in 2 or 3 lines of Python, something like this, just a for loop over the data that you have. In some sense, writing a prior is even simpler, right? You should almost always, for many use cases, your priors are just flat. And so really it's just some kind of step function where you will write, again, 1 line of Python that says, if my proposed data point is between these 2 values, my prior is 1. If it's not, it's 0, right? And so again, this is, or if it's a Gaussian, right? You can just write down a little Gaussian, you can keep that. And so there's plenty of pedagogical value in sitting down and actually doing this, right? This is something that I have my data science students do early in the course when they do this. So yeah, so to this question, there's no right answer, but point number 1, we'd love to see more models in the frameworks that we at least use and apply on ZTF. Point number 2, there's a ton of very popular open source things that are even broader of scope than NMMA. NMMA mostly focuses on, I'll call them sort of more fast transients. SN Cosmo does, mostly supernovae. MOSFET does almost everything these days in some form. So there's a wide variety of these packages out there that I'm sure would love to see these models. However, point number 3, there's a lot of value in just doing this because 1, it's not that hard, and this is all that's going on under the hood on any of these, right? So it's not so bad. Was there a second question, Andrew? No. Okay, good. Okay, so anyways, I just want to take a couple minutes to say, please, I know some of the folks online worked through the notebook yesterday, but I think folks in here mostly did not. And so I just wanted to highlight, this is something to think about this week. All right, so I do see that that Dan is online. And so, Dan, are you ready for your presentation?
I'm ready when you are.
You are ready. That is awesome. Okay, so why don't you go ahead and share? We'll do this. Oh, Dan.
You'll need to give me the screen share permissions.
Yep, let me come around here. Jake, do you want to introduce your advisor today? Yeah, that'll be fun. Let me share screen. Participants. Okay, you should be able to share them.
Yep.
Okay. And K Ryan, you're ready for the, or Andrew's gonna, you're gonna record? Oh, okay, all right, sounds good. Okay. Okay, let me move Dan to pull the video. Probably this size. Yeah, Jacob, you want to introduce Dan? I think as long as you are loud enough so they can hear you, it should be good.
So this is Dan Perley, who's both mining case, he's both mining case advisor from John Walton University of Liverpool. So he's one of the main, well, the main researchers on the Bright Transient Survey, ZTF, which looks to classify basically everything from like 18.5 magnitude brighter, getting a complete sample supernovae.
So we're super happy to have Dan, so you should be good to go whenever, and we'll mute ourselves. Thanks, Dan.
Okay, great. Thank you. Yeah, so I've been asked to talk about the Bright Transient Survey, which is one of the Zwicky Transient Facility's big legacy efforts that tethers the amazing capabilities of the ZTF camera to image the whole sky and look for transients with the spectrograph on site and also other spectrographs around the world to actually figure out what many of these things are. And so I'll try to explain some of the scientific importance of that in this talk, with also a lot of detail about how we actually conduct the survey in practice. So let me start by talking about sort of the explosion of transient discovery that's been going on over the past 20 or 30 years and is likely to continue over at least the next 5 to 10 years. If you go back to the early history of the field, supernovae were really rare things. There were only a few that were found per year in the small-scale surveys that were operated at the beginning of the 20th century. This rate increased dramatically with the development of the first large-scale surveys in the 50s, but didn't really change after that, as you can see in this plot here, until around 1990. And that subsequent change was largely due to the introduction of CCDs and the introduction of robotic control systems. So it increased to the hundreds over the next decade and has now reached a rate of at least detecting in some sort of survey-focused time domain imaging around 10,000 supernova per year. And this is going to increase even further with the beginning of LSST in a couple years to of order 1 million new supernovae detected in survey imaging per year. So that's a lot of transients. Lots of people are excited about this, and that's really great. But we do have to ask ourselves, sort of what is actually the point of this? What scientifically do we garner when we detect such enormous numbers of transients? Do we really learn new things, or are we just making our numbers bigger on the spreadsheets? So the reasons that large samples are useful, there are reasons, can be put in a few different categories. One of them is to find new and different phenomena. So we can find 1 million new transients over the course of a big survey like LSST in the future, or tens of thousands of transients in a survey like ZTF. But most of them are the same common types. But we know there are also rarer types of explosions that might exist out there in the universe, the kilonovae, the afterglows, things like that, which we don't have such enormous samples of. And to find them, we also have to detect large numbers of common things. But even among the common things, there's science to be done. There's trends, there's patterns, and there's demographics to study. So some examples of science cases that we might want to get from large samples of even common types of transients, like say type 1As or type 2 supernovae, or the rates. Exactly how common are these things? That can constrain various interesting scientific questions. I'll touch on a few of them towards the end of this talk. Diversity, the kind of range of properties that a type of transient can exhibit. How luminous does it get? How low luminosity does it get? How fast? How slow? Those all constrain the physics and can tell us things about the phenomenon. There's limits on the undiscovered. Suppose the theorist who works in the office next to you says he's got a great idea for a amazing new type of explosion with peak luminosity of -17 in absolute magnitude terms, and he says there should be X number of these based on stellar population synthesis in the universe. Well, you can actually go out to a big survey and look for things with the kinds of properties that he or she says should exist, and see if that theorist is right or not. And the only way you can do that is having a big systematically gathered sample of transients. Environments, basically where things happen, whether it happens in old galaxies or young galaxies, dominated by old stars or young stars, tells you something about the stellar population and the type of progenitor formation channel that produces a particular type of transient. You can also look into things like metallicity. Does this form more readily at high metallicity, low metallicity? That might tell you something about the properties that lead to the production of this type of explosion. And that's another thing that you need large samples, ideally with good systematics. And then there's also questions like, say, supernova cosmology, which is typically done with type 1As, but can also potentially be done with other types of transients. And you need big samples that are gathered in a coherent way to do that as well. So there's lots of reasons why we might want to take advantage of these big samples. But to do this well, we need more than just having them be detected on some images. We actually have to be quite attentive to the details of how we move them from photons on a detector to well-studied parameters in some big catalog that we use for science. And so to do this, we need a few things. First of all, we need to discover them. We actually need to be aware that they exist. And then beyond that, we also need to classify them. We need to know whether that particular source and that part of the sky out there is a type 1A or a type 2 or a type 1BC or something rarer. So we need types and classifications. And we also need distances. We need those redshifts to know what the luminosities are and to do things like cosmology or luminosity functions or a whole variety of things. So we need light curves. So we need lots of repeated detections, ideally in multiple filters. And we also ideally need spectroscopy to get a precise redshift and a confident type. Okay, so ZTF is very good at this. It was essentially built to do both of these things well. I'm sure you have heard a lot about ZTF already in the summer school, so I'm not going to introduce it in detail again for you. I'll just point out some of the key properties of the survey that make it very good for this. So one, of course, is that this camera has a very wide field of view, and with that wide field of view, it can cover a lot of sky very fast and find a lot of transients that are spectroscopically accessible. It also has this filter exchanger that allows it to sort of natively get these detections in multiple filters so that you can get colors. So because it can cover so much area so fast, it can, even in just a couple nights, and so therefore a high cadence, cover most or even all of the accessible sky to the Palomar site, which therefore means it can garner quite nice light curves. So here are just some example light curves of some fairly bright transients. These are all just coming directly out of the survey pipeline with no additional follow-up, no additional hand-holding of the photometry. These just come right from the alerts that are being streamed to various sources. And you can see these alerts have very nice sampling, nice cadence, stretching for periods of many months because the survey is able to cover the whole sky and not drop fields, except for when they move behind the sun. And so that's really nice for having your light curves. And this is just a few examples, but there's many, many more. And there's, of course, thousands now of transients like this, which have such excellent light curves. Okay, but the other aspect of the survey that is also very helpful is it has its own dedicated spectrographic follow-up telescope over on the other side of the mountain, the Palomar 60-inch, which is equipped with a purpose-built, low-resolution robotic IFU spectrograph, a model of which is shown here, which can reach about 19th magnitude for classification in about an hour, depending on exactly what solenoid you consider you need for a reliable classification. And that means you can not just detect light curves, but you can actually figure out what a large number of these things are. Okay, but how many can we actually get to with this spectrograph? So this graph here is meant to sort of give you some idea about how far deep into the magnitude function we can reach. So the histogram here shows the number of reported transients per year over a 2-year period about a couple years ago. And the green curve shows how much time you need to spend on a sort of 2-meter class telescope. That's a little bit bigger than the SED machine 60-inch telescope, but it's right to about the order of magnitude level to classify them. And so you can see the number of transients that are really, really bright, say 17th magnitude or brighter. They don't require very much time, so it's not hard to imagine that we can keep up with that with a big chunk of time on a 2-meter telescope. But as you start to move down to these faint things where you're discovering thousands of things per year, and you need a couple hours per observation to have a chance at the classification, you start to exceed the amount of time that you might actually have on this telescope to do that classification. So we do have to make choices. We can't just classify every single target that is detected by the survey. And there's a couple of ways we can go about this. So one of them is the exploratory mode, where you focus on the outliers and things that look weird or unusual or different, which is good for some aspects of survey science. For example, if you want to push the boundaries, discover a new phenomenon that have very distinct types of light curves. This is a useful approach. And because such things are probably rare, it doesn't necessarily require a lot of telescope time. But the other approach, which is one where you do need a purpose-built spectrograph to even attempt, or at least a large amount of time allocated on spectrographs around the world, is the more systematic survey approach, where you obtain a high completeness by specifying in advance what your selection criteria are, and you make sure you recover pretty much everything in the survey that passes those criteria and get those classifications, so that when you get to the end, you can be sure you really are capturing the whole diversity of the range of phenomena that you wish to study. So the Bright Transient Survey, which is of course what the subject of this talk is about, is an example of the latter approach. So it is an attempt to catalog a complete sample of extragalactic transients, limited only by their apparent magnitude. So it uses the ZTF public survey, the data that can be accessible to anyone and which is streamed in public alerts every night. And its attempt to take those transients, find which ones are extragalactic, and then classify all of them down to a specific completeness magnitude limit. Now, what magnitude limit can we actually practically reach given the spectroscopic resources available to us? So this is a calculation that we made back in the early days of the survey. So before you get to classification, you actually have to catalog. You have to go take this enormous data volume that's streaming to the CCD, and even this enormous number of alerts, hundreds of thousands that's being distributed to the community every night, and figure which of those alerts are actually the real sources of the extragalactic transients. So I'll explain that a little bit more detail in a moment, but I'll just say for now that what we're doing is we're trying to catalog all the extragalactic transients that are being streamed as public alerts down at this point to 19.8 magnitude. We started at only 19th magnitude, but we pushed it all the way to 19.8 starting a couple of years ago. Now then, in terms of what we can actually do with our spectroscopic resources, it was determined based on some simple rate predictions, which I show in this table here, that we can probably feasibly reach 18.5 magnitude at very close to 100% completeness. And so since the survey began in 2018, that has been our goal, which is to classify everything with a few exceptions, which I'll go into in a minute, which are related to observability and so on, down to 18.5 magnitude, and then using any surplus time to go further beyond that if we can. Okay, so that's basically the goal of the survey. We want to classify all the transients that are extragalactic and in the sky and found in public alerts to about 18.5 magnitude. But while that sounds quite simple, there are quite a few complications that arise in practice, which I'll talk about in some detail. So one question is, how do we know what is a real transient in the first place? Again, the ZTF survey uncovers 10,000s of alerts per night. Some of them are variable stars, some of them are asteroids, some of them are flares from unknown new variable stars in our own galaxy, and so on. So we have to be able to sift through all that junk effectively to find the transients that we're interested in. And we have to be very careful about this because we don't want to accidentally start throwing away real transients because we're trying to be very complete and systematic. So this is a challenge. Then the next challenge is actually identifying what is extragalactic. So ZTF finds everything that is new and variable in the sky. That's sort of the purpose of it. But a lot of those things come from within our own galaxy. They are, again, these flare stars, dwarf novae, and so on, which haven't been previously known to be variable. And so they might initially look from like a transient, but really they're a type of rare variable star, which is just quiescent most of the time and just occasionally flares up. And we don't want to spend large amounts of spectroscopic resources chasing after those things if we don't have to, because that draws our attention away from the extragalactic sky that this particular survey, at least, is meant to study. Some other complications that we run into are the challenge that although the SED machine on the Palomar 60-inch is a wonderful instrument, it's quite sensitive, it's tuned to the properties of ZTF quite well, but it's not perfect. It can't classify everything. Some things, the features are too narrow to resolve them and recognize that whether they're from, for example, the host galaxy, from an AGN, or from the transient. Some things fade too fast. They get too faint by the time that we can get to them, and a 2-meter telescope is not enough. Some things just have features that are too subtle, and you need higher signal to noise than what we can achieve with the 2-meter spectrograph and so on. So you do need other resources as well, and we have to deploy those much more limited resources more intelligently. And then finally, there are all sorts of practical complications introduced by ground-based astronomy. We have seasons, fields move behind the sun and become no longer observable. We have maintenance time on both the 60-inch and the 48-inch telescopes. We have bad weather, we have forest fires, we have all sorts of complications. And so we have to make sure that we are not suffering too much from these when we try to identify our ideally as complete as possible classified bright and sample. So we have sort of developed a procedure for avoiding these things and still obtaining a not necessarily uncovering the classifications of every single transient, but at least as many as possible that satisfy a specific, carefully chosen set of criteria. So the procedure basically is shown in this flow chart, which I'll sort of go through step by step, since I know in the summer school in particular, you're sort of delving a lot into things that are going on at the alert level. So I'll start off with a filter step. So as you probably already know, the ZTF public alert stream produces of order a few times 10 to the 5 alerts per night. You know, that's a huge number, and the vast majority of them are not coming from extragalactic transients at all. And so that's such a large number that you're certainly not going to be approaching this by eye. You need some sort of automated filter to actually cut that number down into something that is manageable for human attention. So starting back in the early days of ZTF, we were hoping to write a very, very simple filter where we basically just make a couple of cuts and get that down to a manageable number. It turned out a super simple filter was not exactly enough, and we had to introduce some extra complications, but at least the principles behind this filter are relatively simple. So we cut on requiring that any alert to be shown to human scanners is not by a bright star as identified by proximity to an object with a high machine learning star galaxy score in the database. We obviously cut on magnitude. We originally cut on 19 by 19 magnitude, but we recently pushed that to 19.8 magnitude after some tests show that we can do this. And we cut on galactic latitude. So we avoid the galactic plane because the extinction tends to block the extragalactic transients anyway. And the stellar density is very high, so there's a lot of source confusion. And you just also have a lot of galactic transients there, and not many extragalactic transients. So we're not really scanning the galactic midplane, but we are scanning the rest of the sky. There's also some other things there. So the actual, as the code as implemented is done with a complicated language called MongoDB, but I've converted it to a Python filter here, which obviously you do not need to look at this code, but I'll just highlight that in the end, we have this ultimate cut, which is based on galactic latitude, the brightness of the thing, whether there is a point-like object underneath it. Also requires that the subtraction be positive and not negative, that it pass the machine learning scores for being a real source, that it's not moving, that it's not next to it, close to a known very bright star, and it doesn't have previous variability, and it doesn't have an asteroid match. And so basically, by some complicated code prescriptions, we check all these things, and if it passes all these criteria, we return it, and it goes to the next step, which is to be shown by scanners and examined by actual humans. Okay, so that's the next step, which is human scanning. So at this point, the thing has passed our automated filters, and it's a manageable number so that actual humans can look at it. And what the humans are looking for is to confirm that this is at least potentially an extragalactic transient, which is to say it's not a bogus source, a bad subtraction, a cosmic ray. It's not an asteroid that somehow got through the asteroid filter. It's not obviously an active galactic nucleus or a quasar or a variable star. It is at least potentially, not definitively, but potentially a true extragalactic source. So this is done on ZTF Marshall, which is called Fritz. which is a Sky Portal instance. Human scanners, which we go in weekly shifts, look through this list of things that have passed the filter in the previous night. They see these basic cutouts, which show the new image, the reference image, and the difference between them. There's a bunch of pre-imaging in multiple filters that are colorized from various surveys like Sloan and the Legacy Survey and Pan-STARRS that are also shown. And based on this, the scanner decides, and then of course the light curve, which shows previous detections of the source as well. The scanner decides whether this potentially could be an extragalactic transient or not. So for example, of these three things that are shown here, these have no obvious counterpart in the image. There's no obvious galaxy there. There's a detection a year ago, just a single one, mostly upper limits, then two sort of sparse detections here. So you might conclude this is either some sort of flaring star or perhaps a recurring artifact. So you probably wouldn't save that one. But this one has sort of a series of detections that are rising with time over the past 10 days. No clear detections before that. It's in a galaxy nucleus where we might find an AGN, but at least based on the available evidence, this at least potentially could be a supernova, so you'd probably save it. And so once an event is saved, it's put in our catalog and then is subject to additional analysis. And then after some period of time, a few hours typically, a script will automatically send that to the transient name server to be reported to the general community as a potential extragalactic transient. Okay, now a bright transient survey isn't just about cataloging. It is, again, largely a spectroscopic survey. And so if this passes some additional criteria, if it is brighter than 18.5 magnitude, or the sort of trend of the light curve suggests that it's going to quickly, within the next few days, brighten above 18.5 magnitude, and it doesn't look like an obvious cataclysmic variable from within our own galaxy, which sometimes can be tricky to recognize, but so we save just in case, then it gets assigned robotically to the Palomar 60-inch SED machine observing queue. And so typically about half the sources that pass our 19th magnitude cut look like they are or look like they will brighten above 18.5 magnitude and get put at some priority level, which we have some internal way of deciding for the SED machine queue. And this is also done on Fritz, the Sky Portal instance. We have drop-down menus. We select which program it's under, we specify the spectrograph, we give it a priority based on how bright it is, whether it's brightening or fading and so on. We give an observation time window, and then it goes inserted into the robotic spectrograph queue, and hopefully it gets observed within the next couple nights. And if everything goes well, that observation happens, the data is automatically reduced sometime during the night. A couple different things happen. So the reduction is analyzed by a simple machine learning tool that Christopher Fremling wrote to see if it is a type 1a supernova or not, and to estimate its redshift. And if it is clearly a type 1a supernova by that method, then it is actually automatically classified and reported to the TNS. So here's a case of that where it's been fit against a particular template matching software, and it nicely fits a type 1A. And so the machine learning would probably pick up an event like this and send it to TNS right away. If it's not a type 1A, we do this by eye. We do the templates matching ourselves. We see if that's an obvious type 2 or a type 1BC or whatever, and we send it to TNS manually, although it's semi-automated. We just have to click a couple buttons for this to happen. And that's nice and convenient. But sometimes it's less obvious. You get sort of like a featureless continuum here. So the green spectrum in both these cases is the actual data, or no, sorry, the red spectrum is the actual data, and the green is the best fit template object from a database. And in this case, they match pretty well. In this case, maybe there's some sort of feature here which could be H alpha, but we don't really know. And so we would not be confident enough to actually claim that this is a classification and to report it to TNS. So we probably need to get more data. So usually the first step is to reassign to get more data from the SED machine, particularly if the source is brightening, and we can expect a higher signal to noise observation the next time around in a week or so. And so we might do that. If that doesn't work, we probably need, if in the second classification spectrum is also ambiguous, we probably need to pull in sort of bigger resources, larger telescopes, higher resolution spectrographs to actually determine what it is. So in this case, this was followed up. In addition to a couple of SED machine spectra, we got a spectrum with the double beam spectrograph on the Palomar 200-inch. And it showed a sort of narrow, but with a broadened baseline here, which is kind of a signature of a type 2N. It's a kind of classification that's hard to do with a low resolution spectrograph. And so that 2N classification was established and sent to the transient name server as its final classification for this particular event. And so one way or another, the goal is for absolutely every transient that passes a certain set of criteria to obtain these classifications, obtain these redshifts, and report them. Now, there are exceptions. Some of the things that we end up saving because we're not guaranteeing that they're extragalactic transients, some of those things do end up being galactic. They end up fading very fast. They have no galaxy counterparts, or if you squint at, say, the Pan-STARRS image, you can see what is probably a faint galactic star at that location. Because these are photometrically distinguishable eventually, and because their spectra are featureless and they're all at effectively redshift 0 and they're not part of our survey, we don't necessarily need to pull out the big guns to study these galactic objects. And so once we recognize that the light curve looks like a galactic object, we'd like to stop bothering to get the follow-up of this type of cataclysmic variable or dwarf nova transient, of which there are many. There's a few of these per night that explode in the survey. The other complication is that because ZTF is really covering the whole sky, it also covers parts of the sky that are close to the horizon and are setting and or just rising, which means we find a lot of events that we discover and then they sort of instantly become unobservable. We don't see them anymore because they set behind the sun. Or we discover after a peak just as they're coming up and we only collect a few points of photometry and then they fade away. Those events are not really useful for samples because we don't know their peak magnitude, so we don't know how bright they got or how bright they will get. They're very hard to observe because they have only a short observability window to our classical spectrographs. So it's not worth kind of running around and pulling out all the stops to observe these things that have these sort of terrible observability. They're only up for a couple hours and only at very high air mass. So during the course of the survey, we developed a couple of additional cuts to exclude these things so that they don't artificially drag down our completeness. So the first cut is, we call it the quality cut. This is a cut to require that we actually are able to cover the light curve enough to say something useful about what it is from the light curve alone. So we make sure that the transient, when it was at peak, was observable to the Palomar 60-inch. So it wasn't that super high air mass when it was discovered and when it reached its peak magnitude. So not at very low air mass, or not at very high air mass. And we also require that in the week before its peak observation and in the week after its peak observation, we got at least one observation from ZTF. So it was not a field that observations were stopping. It was not a field that observations were just starting because of sun constraints. It wasn't cut off by the moon moving through. It wasn't cut off by a sudden onset of bad weather that shut down observations at the site for 2 weeks. It wasn't cut off by maintenance. We actually can say something useful about the light curve because it was continuously observing this field on at least 1 week cadence or so around the time of peak. Okay, and that allows us to say some useful things about the light curve, and also happens to allow us to make sure we were able to get it with a spectrograph. And then also we require that the field is not setting by these criteria, additional criteria here. And those are the main things that we require to make sure that we have good light curve coverage, and at least we had a chance to get it with the spectrograph. We also add a special cut called the purity cut, which is an additional step to filter out certain types of variables that are not necessarily obvious at the time of scanning alone. So this is an either or cut. We require one of two possible things to be true for this thing to enter into our sample. So one possibility to keep the transient retained in our sample is simply that it is coincident with a galaxy. So regardless of what the light curve does, regardless of colors or timescales or anything, if it is coincident with a galaxy and not spot on the nucleus, and that's can be quantified if you're interested in the details, we include that event. Okay, so we don't necessarily require any particular light curve features. As long as it's in a galaxy, it's interesting to us. But even if it's not in a galaxy, because we know not all transients are in galaxies, and we know some transients are in galaxy nuclei, we will include it in our sample if the light curve at a very rough, to a very rough extent, is similar to the light curve that we expect from a supernova. So I'll quantify these things here. So if the fade time, the time that it takes to go from its peak luminosity to about half the peak luminosity, is more than 10 days, less than 200 days, or even within this little region here where we allow it to be slightly less than 10 days, we will include it in our sample regardless of its host. And that nicely separates the things that we know to be real transients, these various colored points here, which I won't go into in detail, but there's a legend here if you want to look at it afterwards from the slides. And that nicely separates it from most of the galactic junk that we're not interested in, the cataclysmic variables. Alternatively, we also can cut based on proximity to the nearest source. So things that are very, very close to a catalog source are likely to be AGN, so we don't automatically include those. Things that are right on a very dim source tend to be cataclysmic variables, these blue things, we don't include those either. Things at massive offsets tend to be sort of artificially associated with the galaxy, and it can also be cataclysmic variables from unseen stars. But things in the middle here is the vast majority of the transients. So by requiring one or the other of these, we are able to get basically all the real transients in the survey without throwing anything out, while throwing out a large fraction of the false positives that would otherwise distract us. Okay, so among the things that pass these two cuts, which are shown here by the big symbols, the small symbols are things that don't pass those cuts, just to show that those exist as well, and we do keep track of them. We have very, very good completeness. So down to 17th magnitude, we've classified everything in the survey that passes these criteria. Down to 17.5 magnitude, we have classified 99.5% of the transients. And down to our goal of 18.5 magnitude, we classify about 95%. So we do miss a few, we're not perfect. Particularly there are periods of bad weather when our classification efforts got blocked by losing multiple nights in a row to bad weather, to snow, to fog, to clouds, etc. So we do miss a few, but we're doing pretty good, especially at the brighter limits. Now, beyond 18.5, because that's where we start to run out of time and we just can't classify everything. Obviously, the completeness efforts, the completeness numbers aren't so good, but they're not bad. I mean, 75% is still better than most surveys accomplish. So we're doing all right. Okay, now in terms of actual total numbers, we have a lot of classifications now. So down to the 19th magnitude level, where again, we're not necessarily trying to be complete, but we are trying to classify as much as we can. We're closing in on 8,000 supernovae. And in fact, when you include the types of additional types of transients that aren't traditionally called supernovae, so the tidal disruption events in the novae, we have passed 8,000. And by the time the current extension of ZTF ends, which is going to be sometime late next year, we should have of order 10,000 supernova classified. So that's a huge database of targets, all of which have spectroscopic data, redshifts, classifications, etc., including significant numbers of pretty rare things like these 1AXs, 1C broadlines, superluminous supernova, etc. Pretty much anything out there that you were interested in, there's now some sort of statistical sample that's been gathered with ZTF. For things that pass these high completeness cuts and are brighter than 18.5, obviously that cuts the numbers because you need it to be brighter. You need to have satisfied these set of criteria for not being setting or rising or whatever. But we still have a pretty significant number, more than 3,000 supernovae, and pretty good numbers of all the various subtypes. And our completeness, again, is about 95%. So that's pretty good. All right, so next I'll move into a little bit of surveying the science of these things. I'm not going to go into loads of detail on the science just because this is more to introduce you about how the survey works, but I will talk about some of the things that we can do with a sample of this type. So the first thing I'll mention is something called the redshift completeness factor. This was actually the original justification of starting this survey, and it's meant to answer a very kind of simple question, which is out to a specific redshift for a specific type of a common transient, what fraction of those transients are in galaxies of redshifts that we actually knew about in advance? And this is relevant, for example, to a LIGO follow-up, because if you're going out chasing LIGO sources and you are searching to some volume, and you want to know, okay, how useful would it be to actually subset our list of galaxies to target, because you say you're doing galaxy targeted follow-up. And you want to know what's the risk that you lose the LIGO counterpart if you're only looking at galaxies with known redshift that are sure within this particular volume. So we can address this question by doing this in reverse. We actually take a sample of known transients and we match them up to galaxy catalogs. and we just quickly calculate what fraction of those transients are actually in galaxies of known redshift. And so out to 200 megaparsecs, or about a redshift of about 0.05, which corresponds more or less to the typical LIGO volume for reasonably well localizable transients. We were able to show about 4 years ago that the fraction of those things within galaxies is only about 63%. So it's about 37% of the type 1As at least, which is another class of sort of old transients, not too dissimilar to what we might expect for neutron star mergers. About 30% of them are actually in galaxies whose redshifts aren't known because they're dwarf galaxies. Nobody's pointed a spectrograph at them yet out of a big galaxy survey. So you would indeed lose a significant chunk, but not the majority of the transients of the counterparts if you are only looking at following up things in galaxies of known redshift within that volume. All right, so that's one simple thing we can do, and that's sort of the first thing we tried to measure with the survey. But you can do much, much more. So you can explore all sorts of different things of the types that I mentioned, rates, parameters, et cetera. And so one of the things that we did next after completing this redshift completeness factor calculation was to do a little bit of exploration of what we call the transient parameter space. So parameter space is a sort of general term for making a plot of any two useful parameters that you can measure that say sort of distinctive things about the nature of the transient, of which two of the simplest things that you can measure just from light curves and knowing the redshifts are the duration, which is some estimate of how long it takes the transient to appear and then go away, and the luminosity at the peak, which is the brightest that the transient got at any point in its light curve. And so to measure those, we come up with a couple of metrics. So the peak luminosity is just the peak absolute magnitude in either filter. And so here's the absolute magnitude, here's the light curve. So there's as bright as it got, so we can measure that and put it in absolute magnitude terms. And then for the duration, we take the basically the full width half max of the light curve. So you go down below the peak by half the flux, which is about 0.75 magnitudes. And then you see how long it took from getting to that point until it faded below that point. And whatever filter in this case was the faster evolving one. So in this case, it would be the G band. And you measure the time elapsed in days in the rest frame of that period. Okay, so here is what that parameter space looks like for pretty much everything that we have detected in the survey to date. And so I updated this plot just yesterday, and it includes about 4,000 transients at this point. And there's lots of different things on here, lots of colors, lots of things smeared all over the place. So, immediately to the eye, you might not necessarily see that there's patterns out here, but there definitely are patterns. You can see there are clearly favored regions of parameter space and largely empty regions of parameter space. And of course, there are selection effects that affect this. In a 2-day cadence survey, which is what the ZTF public survey is, we're not going to find a lot of stuff shorter than 2 days. And in a survey that's only been going on for 5 years, we're not going to find a lot of things that are longer than 200 days. Plus, we actually cut against things longer than 200 days. But approximately over this region from 2 days to 200 days, which is all I'm showing you here, we should be reasonably uniformly complete to all different types of transients. So this distribution is actually reflective of real astrophysical preferences in the transient population. And furthermore, you can see that different colors, which are different spectroscopic classes, have their own internal preferences. So this really is a real effect. It's showing real physical phenomena. So actually putting on into more detail at some of these classes, I'm not really going to go into detail of the physics that determine all these things, but basically where a transient appears on this space is a combination of lots of different things. It's the velocity of the ejecta, how opaque it is, whether it's light elements or heavy elements, how much mass was expelled, how much of it was radioactive, and how big the progenitor was, whether it was surrounded by circumstellar medium or not, and whether it produced some sort of central engine that kept pumping energy into the ejecta from inside, something like a neutron star or black hole. All these things affect where a transient lies on this parameter space and are things that you can explore by examining these trends. So just to show a couple examples, you've probably heard that type 1As are standard candles, which is not entirely true. They're standardizable candles, and they're not perfect standardizable candles. They do have internal scatter, which is partially corrected for by light curve metrics. And so you can see here, type 1As are only occupying a relatively small region of the parameter space. That's testifying to their standardizability. And there is a slight trend between the duration and the magnitude. The longer ones are the brighter ones. That's the famous Phillips relation. But there is quite a bit of scatter here. There's rare subtypes, there's fast types, there's long types. And then there's this interesting event up here, which seems way too luminous than you might think is a data problem. But actually that event is a gravitationally lensed event, which is 2 or 3 magnitudes brighter than it ought to be because it's being magnified by a foreground galaxy. So in addition to finding large numbers of things just by going out and getting their classifications, you find small numbers of curiosities like that when you do a survey like this. So while type 1As are an example of a transient that longer lived events are brighter, type 2s, which is another common type of transient, actually show the opposite event. The longer lived events, which are much longer lived than the type 1As on average, are actually fainter. And that's a reflection of the different physics that are involved between these two types of transients. For the type 2s, it's largely a question of mass, where with type 1s, it's largely a question of amount of radioactive elements produced. And there's also a subpopulation of type 2s that are very fast, which probably reflects light curve being driven by shock breakout as opposed to radioactive decay. Type 1bCs, the sort of the third major supernova subtype, show yet another trend. So the typical 1bCs, the sort of classical ones that show classical 1bC spectra, and are the only type that was known about before the mid-90s, kind of just sit in the middle of parameter space, don't have a huge amount of internal variation, but there's sort of interesting subpopulations that exist that extend in various directions. There's a subset of very long-lived type 1bCs, which actually have an order of magnitude longer timescale to appear and disappear compared to normal 1bCs. There's the subset of 1C broadline events, which is spectroscopic class that tends to be a little bit more luminous. There are fast 1bCs, which tend to be underluminous in most cases. And then there's this subset of superluminous hydrogen poor supernova, which are much more luminous and also much longer lived at the same time. And so all these things are reflective of the physical phenomena that drive these different types of transients. There's also rare things that are not what we consider simple supernovae, because they're not explosions, not necessarily explosions of massive stars. There's these underluminous things that are called intermediate luminosity red transients or intermediate luminosity optical transients. We don't know for sure what all of them are. Many of them are probably stellar mergers. Some of them could be electron capture supernova. So that's sort of an active area of investigation. There's many tidal disruption events. So there are classification large-scale survey papers coming out on the tidal disruption events in ZTF, examining some of the trends within this population. Some of them can get remarkably luminous, almost up to -24 absolute magnitude. There's this new group of things called fast blue optical transients, which come and go in just a few days. We're trying to figure out exactly what those are. They tend to be quite luminous themselves. And we don't know what we'll find next, but probably there are going to be new phenomena which appear in this parameter space if the survey keeps going for long enough as well. So lots of interesting things there in the parameter space. Some other things that you can do are measure rates as a function of magnitude, which is another way of saying the luminosity function. So for a given class of transient, if you have a large enough sample, you can break that transient down by the peak luminosity, and you can determine the rates of different transients of that class as a function of their peak luminosity. So for example, for type 1As, again, they're fairly standard. They have a very clear, well-defined peak at around an absolute magnitude of -19, and they fall off pretty fast on either side of that peak. Core collapse transients, supernovae, are less luminous. Their peak is characteristically around -16.5 and fall off more slowly. So for example, core collapse supernovae do exist out to very high luminosities. These are the superluminous supernova here. And there is also a tail that goes down to low luminosities, which we don't probe as well because because you can only see these things out to a small volume. So we only have a handful down at this low luminosity rate here. If you integrate this luminosity function, you can measure the rates of these types of transients. So you just integrate it up and you apply some corrections based on your known area of the survey, your completeness fraction, your sky coverage, et cetera. And you can calculate these things in terms of numbers of explosions per cubic gigaparsec, so per volume of space per year, and calculate what those are. So we get rates that are similar to current constraints in the literature for type 1As. and likewise for the type for the core collapse supernovae, about 7.8 times 10 to the 4 per cubic gigaparsec per year, which if you compare that to the rate of star formation, that corresponds to about 1 supernova exploding per 200 solar masses worth of material that has gone into newly forming stars, which is approximately consistent with what you would estimate if you take an initial mass function, you look at how much mass is going into big stars, you look at the initial mass function of those big stars greater than 8 solar masses, and you get about 1 supernova in that part of the IMF formed per 200 solar masses of material. So that's reasonably consistent with what we would expect from galaxy formation, galaxy and star formation observations. So that's nice. We can also break that down by subtype to explore exactly what it is that makes different core collapse explosions take different types. So for example, about 75% of the core collapse supernova by volume are of type 2 and 22% are of type 1bc. And you can break this even further into some of these rare super subclasses as well. And for example, if you were a firm believer that the absolute only thing that controls the destiny of a star is the initial mass function, you might be looking to subdivide this initial mass function as a function of progenitor mass and sort of chop it up such that the most common thing is the lowest mass and the less common things are various subdivisions of the higher mass stars. And if you were a firm believer in that, you'd have to conclude that type 2s go up to about, let's say about 30 solar masses here. Type 1bc's would then go about to 100 solar masses, and these other things would be the rare things that are going up above 100 solar masses. That's what you'd have to conclude. But that probably wouldn't work because we do also know now from surveys of the Milky Way and the Magellanic Clouds that only about 30% of stars remain single and don't interact with their binary companions over the course of their life. Actually, most companions do engage, most stars do engage in interaction with their companions. And so even among things like type 2 supernovae, this shows you that because they're 75%, but only 29% of stars are effectively single, probably a significant fraction of type 2 supernovae do undergo interaction. And that means these rare subtypes are likely being affected significantly by interaction, envelope stripping by a companion as well. And that's something that you need to know confidently what the rates are to really address in detail. So this is a launching off point for explorations of to what extent the combination of initial mass, binary interactions of various types control what the ultimate outcome is that you get for a core collapse explosion. Other things we can explore are things like host galaxies, just what type of galaxies do different types of transients explode in. So in these plots here, I show the peak the luminosity of the host galaxy in the I band here. So things on the right are the more luminous galaxies, things on the left are the less luminous galaxies. And the color here, so blue galaxies, classical star forming spirals are blue and so appear towards the bottom. Red and dead galaxies with very little star formation appear towards the top. You can see here, the grays are things from the Sloan Digital Sky Survey. There's sort of two classical populations, the blue cloud, which is the spirals and the irregulars, and the red sequence, which is basically the ellipticals. And you might wonder what fraction of different types of transients come from blue clouds, red sequences, and so on. And that's something we can address in the survey. So for example, for type 1As, it's roughly 50-50 or about 60-40, 60% come from the red sequence, 40% come from the blue cloud. And the typical luminosity of a host galaxy is around -20.5, 21. And that more or less matches what you'd expect if the star formation, or not the star formation, if type 1As are produced more or less uniformly with the stellar mass of their host, which is shown by the dotted line. So they more or less track with some slight differences, the stellar mass function of their host galaxies. Whereas, unsurprisingly, the core collapse transients don't happen so commonly in red sequence galaxies, which don't have much star formation. They primarily originate from the blue cloud down here. And instead of following the stellar, they don't follow the stellar mass as well, but they do follow the star formation rate pretty well, which is not shown here. And there's no big differences in this sample between, say, the type 2s and type 1bc's, but it's a point of future investigation to see if there are more subtle differences with larger samples in where type 2 supernova, which are non-strip stars, occur versus where type 1bc supernova, which do come from strip stars, and where those occur, since that might be affected by metallicity, age, and various other things. Right. So that's just a teaser of the kinds of science that we can do and the types of science that you in principle could do if you wanted to dive deep into the future and exploring what can be done with very big samples of very systematically classified transient populations. The lessons here are that we don't necessarily have to classify everything to do a big survey like this. We just have to classify all of some subset of criteria that have been established in advance and have been checked carefully. Survey and spectrographs have to work together in a consistent, sustained way to do this well. To escape the systematics, we do have to go understand how our filters work, how our scanning process works. We have to do lots of checks, and we have to write down what our rules are for what we classify and what we don't classify, and make sure those rules are satisfying what we want them to do. And we have to pay careful attention to selection to do these sorts of science, demographics, rate, host galaxies, etc. So I'll close with a bit of an advertisement for some of the public resources that we've made available. I'm sure you all already know about how to access ZTF alerts, and you've been working with them a little bit already. And so that's a great starting point. But if you want to sort of skip ahead a few steps and actually go straight to doing science exploration from these subsets of classified transients that we have, there is a website for that as well that we're serving to the public community. It's shown here, and you can go to it after this if you're curious, or even just type it in right now to explore. And in particular, I like to advertise that we have an interactive live catalog that you can go to, which serves images of the light curves, classifications, and even host galaxy properties and quite a bit more at this link here. Just to show you some examples of what you can do with this link, you can filter by redshift, by position on the sky, by how long the light curve duration, rise time, fade time, peak luminosity, as well as even the host galaxy properties, and come up with interesting subsets of transients of various types of your own to go ahead and explore their properties. By default, it will show you a catalog in your web browser, but you can also show it as do it as a CSV file and do your own calculations on that in Python or whatever other language you choose. And if you like looking at pretty pictures or you like looking at light curves, you can even choose to show those as well and display them as nice grids to explore just what it looks like when a transient goes off in various parts of the universe. Okay, and that's everything I prepared. Thanks for your attention.
No, now clap. Yeah, there we go. We're too slow. Yeah. Okay. Thanks, Dan. That was awesome. Questions from the crowd or on Zoom? Okay, we got one from the crowd.
Can you hear me from here?
Yeah, I can hear you fine.
Cool. Thanks for the great talk. I was wondering, with your automatic classification of the type 1A supernovae, do you have an estimate for how many of the regular type 1A supernovae that get classified are actually possibly 91BG like type 1As?
I do not know the answer to that. So that method is really developed for normal type 1A supernovae and not sort of the rare subclasses, which we tend to want to examine in detail ourselves anyway. And the threshold for which it chooses to establish a classification or not is set to be very, very pure, since we don't want to be artificially reporting things that actually aren't type 1As to the TNS. So yeah, I unfortunately don't have the statistics for how well it performs on sort of the uncommon subtypes like the 91BGs, but you can pop the author of that method an email. He's Christopher Fremling, if you're curious about that.
Thank you.
Question in chat. I saw Sarah's go by. Sarah, do you want to just speak up and say your question?
Okay, sure. I was wondering who makes up the team of scanners, and are there any grad students in that team?
Yeah, so it's sort of varied over the course of the survey since we've been doing this for 5 years now. Sort of definitely the main legwork traditionally has been done by graduate students. And so, both of my graduate students who are there with you today have been doing a lot of scanning work. I did a lot of scanning myself, particularly in the beginning. Christopher, the other sort of lead of the Bright Transient Survey, has done a lot of scanning himself. Various graduate students that have come through Caltech have done quite a bit of the scanning. And Eugene Quinn, our new postdoc, is doing a lot of scanning now. Jesper Solerman in Sweden, he's a professor there. He really likes scanning, and so he does a lot of scanning. So yeah, so it's like all kinds of people, all the way from the grad student level to the PI and professor level. In addition to that, we actually have two different filters running. So something I didn't mention is that we actually have two versions of the filter. There's one that is still set to 19th magnitude as its brightness cut, and then there's the one that we started in 2020 that actually goes all the way down to 19.8 magnitude. And that deeper filter is primarily scanned actually by undergraduates. So we check up on them to make sure that they're doing it right. But the majority of the work on the deeper filter that's going beyond the range that we do the spectroscopic classifications for, but do put in our catalogs, that's actually primarily being done by even by undergraduates right now, primarily at Berkeley.
Sounds cool. I'm glad you're getting a lot of engagement at different levels.
I'll also make a plug for, so in the next talk, we'll be talking about Nabil's stuff, who's also at Northwestern with Sarah. We'll be talking about the automated ML-based scanner that one of the graduate students is building, and there's some info on that, or we're going to play around with that a little bit in the notebook for today. So that should tie in trying to get rid of human scanners and so on. Okay, I did see, let me try to move these over. I don't know. Okay, who's up next? Like this. So there's a question about, in addition, so Dan, there's a question in addition to the website that you showed, there was also the question of kind of, is the code to produce some of this stuff available on GitHub, or how available are these data sets and, code to pull down data and all that fun stuff based on, like in your Explorer and so on.
So for the original filter before it migrated over to Sky Portal when it was still using our previous Marshall. So the basic filter code of that was put on a couple places online. I think it's on GitHub and other places when we published the original paper with the first 2 years of the catalog. So the updated that filter was then migrated to this MongoDB, and then it was migrated back to Python for what I showed you there. So we don't have a posting of that translation yet, but it basically does the same thing. So yeah, so we should probably put that online sometime in the near future. Kind of like the code that serves these websites and so on, and has been doing the more detailed processing. That's not public yet, but that is an aim to share that in the future. Obviously, the Sky Portal is Michael, correct me if I'm wrong, but I believe all the basic code for that is public, and that's obviously a much bigger thing that does all this alert processing and so on, but it is there. So much of it is public, but some of the details aren't yet.
Yeah, all right. Thank you very much. I'll go through the online resources that are right now available at the website. And yeah, sure.
Yeah.
Thank you.
So there's another question in the Slack that's really focused on how do you deal with sort of the fact that you have these transients and they're setting soon. So how do you do kind of this, rapid global follow-up stuff?
Well, so largely it's through the procedure that I outlined. So we just have a lot of people that are, obviously saving the transients and assigning the transients the first time, but we also have sort of weekly meetings where we've also developed websites that kind of scrape this transient list and say, okay, there's this list of 20 transients that haven't been classified yet, and it looks like they are on track to pass our selection cuts. So you better get classifications of those. So there's a website that I wrote that anybody in the team can go to and look at those and say, we better check those. When classifications requests expire on the SED machine, if a spectrum doesn't get taken, you get an email, and ideally that person should then refresh them if they still think it's an interesting extragalactic transient. When a spectrum is taken by the SED machine, you also get an email that sends you to the reductions, and the person is supposed to look at those reductions. And if the classification doesn't satisfy, it isn't obvious from that, you're supposed to put it in a second time unless it's no longer meeting the selection criteria. And yeah, there are people who are nominally meant each week to be keeping an eye on this independently of the people who saved it. So there is sort of a whole semi-informal but partially formalized procedure among sort of the core 5 or so people on the team to keep, you know, so to keep this process going. And it's in particular, just sort of when we do need to turn to classical runs to make sure that we're sending the people who are doing the observing, which is also quite a bit of work, which is largely Caltech grad students who are doing this, the targets that we need them to get, and then for them to reduce those quickly to make sure that we really did get the classification and don't need to escalate it even further.
All right. Any other questions before we take our break? Okay, if not, let's thank Dan again. It was really nice. Okay, so we're on break till 11 local.